Welcome. My name is Dr. Dave Turner. This is an introduction to the BeoShock compute cluster at Wichita State University. Um, our group is at Kansas State University, but we manage both the BeoCat supercomputer system or cluster computer uh, at K-State, and we also manage the compute cluster at Wichita State University. I want to start out by talking about what a supercomputer is, and that's definitely changed over time. Uh, Back in the early days, in the 70s and such, a computer was just a scalar computer. It had one compute core, it did one thing at a time, and it was a lot easier to understand. And in the 80s, we got Cray vector computers. These were made instead of from silicon chips. They were made with gallium arsenide chips. They were faster. They were vector processors, so they did 64 things at a time. So if you had a loop, for example, it would pipeline things so it would do things 64 at a time instead of one at a time going through that loop. These were often $10 million machines. They were water cooled. They were expensive and hard to work with. In the 90s, people started building cluster computers. And what that is taking PCs or more often high-end servers and putting them all in the same rack and connecting them with fast networking and a common file server so that you can run one job on multiple compute nodes if you program your job to work in that way. This eventually went to where instead of each compute node being a scalar computer, each compute node had multiple cores, so you could get parallelism within a compute node as well as job running across multiple compute nodes. So multiple levels of parallelism made things more complicated, but meant you could extend the power that you could apply to a single job. After that, GPUs or graphical processor units got mixed in there as well. While GPUs were primarily designed for doing graphics, in a supercomputing environment, we primarily use them to speed up scientific codes. So they are streaming processors. They're good for graphics, but they're also good for running certain types of applications. So let's get started with the BeoShock compute cluster. And I have a diagram here. If you log into the cluster using SSH from a terminal window, for example, you'll get dropped into one of the two head nodes, head node 1 or head node 2 in the upper left of this diagram. That's where you start and you can modify input files, you can modify your code, things like that. That's where you'll create your job scripts that you'll submit to the Slurm batch scheduler. The head nodes and the compute nodes all run Rocky Linux. Linux is a type of Unix. It's very common these days. So most cluster computers use a flavor of Linux, and it doesn't too much matter what type of Linux it is. The Slurm batch scheduler is also very common. So once you learn it on BeoShock, you'll be able to use that knowledge on a lot of other remote resources that you may have access to as well. The batch scheduler the idea is that you create a job script that tells the scheduler what resources you need, how many nodes, how many cores, how much memory, that kind of stuff. And then the second half of the job script will have the commands that you want to run on that compute node or nodes. And we'll get into this stuff more in depth later. BeoShock has 768 Intel cores on 21 compute nodes. So 21 compute nodes, again, a compute node is a high-end server or workstation, just more powerful than your normal PC. And these have Intel chips in them. The colored boxes down at the bottom show the different ones there. There's 16 compute nodes with 36 cores each and 186 gigabytes of RAM memory each. And then there's 2 GPU nodes, each of which has 2 NVIDIA V100s. And the GPUs have 16 gigs of GPU memory on them. And these nodes have slightly more memory on the CPU side than the compute nodes. They have 375 gigabytes of RAM memory. The physics group purchased a node themselves, so they get high priority on the one node in red that has 4 NVIDIA A30 GPUs with almost 25 gigs of GPU memory in there. And these have 48 cores, while the others have 36. And these are also large memory machines with 515 gigabytes of RAM memory. And then there are 2 high memory nodes that are accessible to everyone, 36 cores, but here we have 1.5 terabytes of memory on each. A terabyte is 1,000 gigabytes. So all told, the BeoShock compute cluster has 7.2 terabytes of RAM memory on all 21 nodes added together. And these are connected with a 10 gigabit per second Ethernet network that's very low latency. And if you were going to run a job on multiple compute nodes, then you would be using that network to communicate back and forth while your job runs. There is a common file server that's mounted on all 21 nodes. It has 150 terabytes of space. That's a lot. Most users will use about a terabyte or less. If you are going to use more than a terabyte, then we ask you to get in touch with Terrence Figge and get his approval, just because this is a limited resource shared with others. Again, I've gone through the GPUs there. Mostly you would access these compute nodes through a batch script submitted to Slurm. There's also available an interactive approach going through on demand. That's a web-based graphical interface, and we'll go through that as well. Okay, the administrators, the ones at Wichita are on the upper part here. Terrence Figge is the director of high performance computing. Ryan Dahl is the data center director, and Anita Barrett is the ITS director of project management. As I said before, our group at Kansas State University administers the BeoShock cluster as well as our own BeoCat cluster. So they're very similar in nature, and that makes it efficient for us to kind of duplicate what we do at K-State at Wichita State as well. Nathan Wells is our system administrator. We have an open position for an IT architect that we're looking to fill, someone that will help him. And then I'm more user-facing. I'm the application scientist, so I deal a little bit more with user and programming issues and performance issues and things like that. And then Seth Gallitzer is our computer science system administrator. He's actually got a different title now. He helps out with us at times as well. To access BeoShock, if you don't have an account already, you have to start with Wichita State University ID, and that gives you VPN access. Once you're logged into the VPN, you follow that link there to get to the HPC guides, and then you follow the click on the link that says obtain an account and new user request. I'll show you those just briefly. So this is, again, the HPC guides. This is the page that you land on. And right at the top is the access and login, where you see obtain an account. You just click on that to expand it. Click on new user request, and then you fill this out. And again, you'll submit it, and then it may take a day or two to get a response and to get it to get your account set up in that. Then there's also documentations here on how to connect. If you have Linux, if you're sitting on a Linux laptop or desktop or a Mac, then you have a Linux terminal that you can open. On a Mac, for example, there's an app called Terminal, or I have iTerm2 apps that I like a little better that I've installed. On a Linux system, you just, again, open up a terminal window, and then you SSH in, like this highlight here, using your WSU ID here. So you replace that with your particular WSU ID, and then put at hpc-login.wichita.edu. And again, that'll drop you on one of the head notes. For instance, this is my WSU ID there. So in order to get here, I would normally have done an SSH of this WSU ID and then at hpc-login.wichita.edu. On a Windows system, you can install PuTTY, and then everything's going to be similar in how you SSH in. If you're going to use the system a lot, I would recommend installing MobaXterm. That gives you a terminal window, but it also allows you to sync up your files more easily between your Windows system and the HPC Linux system. In this way, you can start by editing your files on the Windows side where you may feel more comfortable. And then you can move that over to, you can sync them up with the Linux side a lot more easily than if you had to edit your files on the Linux side. Okay, I'm going to pause here. The remaining slides are similar on BeoCat and BeoShock, so I'm only going to do them once. So I'm going to pause and then do the intro to BeoCat side, and then I'll continue and splice the remaining presentation onto the end of both. Okay, as I mentioned, probably the normal way to use a cluster computer like BeoCat or BeoShock is to SSH in and use the command line. But we also provide the open on-demand, a graphical system for getting on the nodes and using them as well. This is a web-based system. So for BeoCat, you would use this top command, and then the next one down would be for BeoShock. Otherwise, the usage is identical. Uh, you would log in with your credentials, and then you may uh, need to use duo authentication as well. And then under interactive applications, you can request, for example, a BeoCat or BeoShock desktop environment. This provides a more window-based view where you would have folder icons, for example. And I'm also going to give a demonstration of interactive Jupyter notebooks. A lot of people who do Python development uh, like to do the development in Jupyter notebooks because you get immediate feedback. And so it's a very good way to develop your code. But in the long run, we do like it if you convert that over to normal Python or save it in Python files and run it from Slurm. So let me start by showing you an example. And I'm going to do this on BeoCat. So we want ondemand.beocat.ksu.edu. And I've already logged in today, so I did not get prompted for my KSU EID and Duo. So you can go under clusters here and get a shell, just a raw shell. It's more common to look at things under the interactive applications. If you want to just get a BeoCat desktop, you can click on that. And anytime you do anything on demand, you need to request, fill out the form here. This has defaults of 24 hours, 1 core, 10 gigabytes, and it says interactive job. If you're requesting large amounts of resources, you may have to wait, and you might want it to email you when your job is ready to run. Here we're going to say launch. Now we've requested the resources, and it does say please be patient. Since we've only requested a little bit, 1 core, then it should come back pretty quickly. Again, if we requested 500 gigabytes, or if we requested a GPU, it might take a lot longer to come back, including a couple hours, because it has to get scheduled the same way a job script does from the command line. So it's got it running. It says running up here. So click on that to launch the desktop. And it has a terminal up here. I'm going to move that down to the bottom. And you can see that I have a variety of desktop folders now. So in the terminal window, I can do an ls, and I can see these same things. Like I have an apps directory there. I have a folder here. And if I double click on that, it should expand it and show what's in my apps directory, just the same way as if I did a ls of apps down here. So it's just a graphical view with folders rather than a command line. And so if you're more comfortable doing some things like moving files around, you can certainly use this. I'm going to go ahead and kill off this window. That does not kill the job off. This will keep running for 24 hours total unless I cancel it. I'm going to leave it running because I want to show later on what I have running at this moment. And it'll show that I have a couple things from on-demand running. Let me show you then there's some other uh, special programs that you can run, like Mathematica that we have installed already, Octave as well. The most common thing that people run, though, is Jupyter Notebooks. R Studio is down here for people who program in R and want a more graphical environment as well. So that's pretty common too. But if we click on Jupyter, again, we have to request the resources. The default, again, is going to be 24 hours, one core, in this case, 4 gigs of memory, interactive. Uh, some Python stuff does use GPUs, so you can request a GPU there. And again, you can ask it to send an email when it starts a session. We're not going to do it since we're just asking for a minimal amount of resources. So let's see. So again, it says, please be patient. So again, on demand is very good, especially Python. Jupyter Notebooks is very good for developing applications. But we do like to see everyone eventually move to job scripts. If you have if you're running things interactively and getting to production runs, the problem is that if you ask for 24 hours and you do a production run with on demand, then if your job gets over 12 hours in, it doesn't cancel off your on-demand sessions. So your resources are still locked up. So other people can't use those resources, even though your job is done. Where if you use a Slurm batch uh, job, then when your job is done running, it releases all those resources. So I click here to connect to Jupyter. And then you go over to New. I actually did a setup of my own virtual environment and put TensorFlow in there. This is more sophisticated, so I'm not covering this until the advanced presentation. This is always there. This is a Python 3 kernel, so that's what I'm going to choose now. And when that comes up, this is our Jupyter Notebook. So we can actually put Python commands in here, like print. And then in order to run that, we have to click on the run up here, and we get immediate feedback here in that it printed out hello world. So in this way, you can build up all your Python commands, and then you can save it at the end into either, you can save it as a Python a notebook file, or you can convert it into a Python script. The Python script is how you would want to save it if you, yeah, right there is how you would save it if you wanted to save it in a .py Python file that you could run from the command line, for example, in a Slurm job script. But otherwise, if you're going to continue developing things here, you would want to save it as a Jupyter notebook. From the notebook, you can also do command line commands like my ls command. Oops. And then you can run that. And it again does the same as if you're typing it into a terminal window. It listed off all the different directories that I have in my home directory, like the apps directory that I showed you. So that's just a very rudimentary introduction to Jupyter Notebooks. Again, I'm going to get out of this, but this does, just clicking on the tabs to get rid of them does not cancel my sessions. In order to cancel the session, I'm going to do my desktop one. I would click on that and say OK. And at this point, it's canceled. So I still have the Jupyter Notebook going, and that will run for 24 hours or until I kill it. The Beocat desktop one is done. This just shows that there's still a listing there, and I'm going to delete the listing, even though the job is actually done. It'll just clean up this window. So that's a very basic introduction to on-demand, the graphical interface to Beocat. The rest of this presentation is going to concentrate more on the command line interface. So what you do when you SSH into the head nodes and how you operate. So one of the things that you'll need to do is to be able to monitor the nodes on Beocat or BeoShock and be able to tell what jobs are running there, especially your own jobs. And Slurm provides some tools. There are some commands, SQ and saccount, but they're very clunky to use. So over the years, I've written up a Perl script called kstat, and that takes information from SQ and saccount, but also from different resources like the /proc file system, where it gets the amount of memory that you're using. And it even looks at the graphics cards if you're using one and probes those and gets information on the memory usage and the utilization for those. And it puts it all in one place. It colorizes it. Colorizing means if you see something in yellow, that's probably a warning. If it's in a red, that's definitely something to pay attention to. That means your job is probably doing something wrong. And if you can't figure it out, you should probably contact us. Basically, you should use kstat ---- help to give you an idea of how to use it. So on Beocat, I'm going to do that. And that is going to return basic help information. So again, if you do kstat, it'll give you a listing of all the compute nodes and all the jobs running on those nodes, and also the jobs that are queued. If you just want some of that information, you can do a kstat -h that will just list the host information and not the jobs. And you can also sort and only pick out one type. So if I just wanted the AMD processors on Beocat, those are the warlocks, is what we have them named. So if I just want to look at the host information on the warlocks, I would use -h. And this tells us that we have 37 warlock nodes. The last 4 are still being set up here, so they're currently down. Some of the others are draining for various reasons. You can see different information about each here. This has 28 cores being used out of 32. This tells the load is only 20. So that concerns me a little bit. When the load is 20 and we're running 28, the load really should be at least 28. So that's underutilized. This is the amount of memory. This is the total memory. This is the memory used. This is the memory allocated. This is the owner of the node. So Professor Cook owns this node. That means that they get priority. They and anyone in their group gets priority. Anyone else can run on those resources when they're not being used. But if someone from their group gets on, it will kick your job off. It will get automatically requeued and run on a different node. But that's what the orange means in jobs on Beocat. On BeoShock, the nodes are named a little differently. The compute nodes are prefaced with the word compute, and then we have GPU and then high mem. But likewise, you can see most of these nodes are filled. The dark blue means they're filled, 36 of 36 cores. The load is 36, which is great. The memory is 50 gigs is being used out of 55. And the total memory is 186, but that means people are requesting right about the correct amount of memory. So I'm kind of curious. I'm going to look at that one node. I'm going to do an L for a long list and then do compute 201,904, and we'll see exactly what's running there. One person is running on the magenta means it's a multi-node run. So they're running on 36 cores of this node plus 36 cores of some other nodes as well. But it does mean that they're doing a good job of requesting. They're using 50 gigs of memory, and this is the maximum, and they're requesting 56. So they've done their homework and they're requesting the right amount of memory. This I don't like to see. It means they're only using a quarter of the 36 cores that they've requested. So when I use KStat, this would tell me that I need to look more closely at how this person is using. They're doing some things great, but here they're only using a quarter of the 36 cores. So I would look into that further. If you do a KStat, let's do this on BeoCat because there's a longer queue. If we do a KStat minus Q, this is going to show you just what's in the queue waiting to be run. Anytime you see OSG, that's Open Science Grid. These are jobs from outside the university. They run totally in the background. So any jobs that's on BeoCat and BeoShock. So they soak up the extra cycles so that our systems remain pretty much full and doing other people's science. So that's good. So the queue on BeoCat is actually fairly short at the moment. I need to talk to these people because they're requesting 2 nodes, 60 cores. No, those will work. But they've been waiting 20 days. They're doing something wrong that I'll have to look into. So this is a good way of seeing how much time you should expect to wait by what's in the queue and seeing when your job is at the top of the queue and should be running. If you do a KStat minus C, that'll give you another view. This will tell you who's using the system most. And on BeoCat, we have this one user. I highlight in yellow anyone using more than 5% of the cores. They're only using 152 cores. And again, we have 10,000 on BeoCat, so that's not much. So at this point, we have a lot of our cores not being used. We've just started the summer, and a lot of professors may not, and graduate students as well, may not be in full swing for this summer. This is the GPU utilization down there. And again, we have about 170 GPUs on BeoCat, and we're only using 43 at this point. So a lot of space open at this point. If we do a KStat, I'm going to do a minus me on BeoCat. It's going to tell me what jobs I currently have running. And this is a good way of just looking at your own jobs. And what this says is I have one on-demand job running. And that's the interactive. And this is on one of the 4 interactive nodes called Gremlin. And it's been running for 13 minutes. So I would have to normally go back and kill off that session. I'm going to do it manually by using the job ID number. Every job has a unique ID number. That's how you reference it to look more in depth on it or to cancel it. So that should have canceled it. So now when I look and see what's there, I should have no jobs. If I want to look and see what jobs I've run in the last 10 days, I do a minus D10. This is extremely useful. Uh, if you had something go wrong or you weren't sure, uh, you can look back and see this job that I ran here ran for 1 day and 23 hours, 31 minutes, and it completed. It was on 32 cores. It tells you how much memory uh, I, I used, and I clearly requested a lot more than I actually needed. And then these other 4 jobs are on-demand jobs that I've done today, and I ended up canceling all those. A few of them I did for test, and then these 2 are the ones that I showed you. So this is a good way of looking things up. If your job fails, you'll often get a message. It might be out of memory. Well, it'll say out of memory here as well, or it'll say failed, and you look in your output file to get more information. Okay, so let's move on. K-Stat's very useful. And again, it colorizes things to try to give you helpful information. Okay, so how do you submit a script? Uh, I have this test script on both BeoCat and BeoShock. Uh, you can copy those over from my home directory at the paths on the top there. The actual script is on the right. Everything that's preference. So first of all, the pound exclamation is called a shebang. The /bin/bash says that we're using the bash shell. Uh, the bash shell is probably the most common used in Linux. You can use CSH for the C shell as well if you want, or SH for the Bourne shell, but bash is the most common. And that's what I'll use in this presentation and also in some of the more advanced ones. We'll cover Linux and the bash uh, shell scripting in particular. So everything that's prefaced by pound and then capital S batch is information that's going to go to the Slurm batch scheduler to let it know what resources we're requesting. So the top thing there, the minus job name, is doing just that. I'm going to name this job hello, and you can name it anything you want. A lot of times people will name it by the application they're running or by the particular experiment. So AG25 might be a simulation of 25 silver atoms, for example. I was talking to one graduate student once, and I told her she could name her job anything she wanted, and she couldn't come up with anything. So I suggested, well, you can name it Fred if you want. And so we put Fred in there, and I was just kind of joking around, and she just kept it in there. All her jobs for the next 2 years were named Fred. So I guess I should be a little more careful when I joke around and say that. You can name it anything you want. This one is just saying hello, so I named it hello. The minus time is how much time we're requesting. In this case, it's days dash hours colon minutes colon seconds. So we're requesting 1 hour of time. If you don't put a minus time or any of these others, it'll default to something that's probably shorter than you want. The nodes is the number of compute nodes. The n tasks per node is asking for one core. So we're asking for one core on one node. If you know that your job can run on multiple cores within a given node, you can request more than one task per node. If you're going to do that, you should test your code out and make sure that if you're running on 4 cores, for example, it will hopefully run close to 4 times as fast. So you want to do a scaling test to see that you're getting good performance out of those extra cores. Again, if your code is capable of running on multiple nodes, you can also request multiple nodes, but it has to be programmed to do that, to take advantage of that. Then you request the amount of memory you need, which is 4 gigs right here. The most common question we get asked is, how much memory does my application need? And we don't know that. Mostly when you're starting with a new program, or even starting with a different input file that might take more or less memory space to run, you should ask for more memory than you need and run it and use kstat -L to look at your job, and it will tell you how much you're using exactly. And then if you've over requested by a lot, you can kill your job off and requeue it with a more reasonable amount. 4 gigs, all our systems have at least 4 gigabytes per core. So if you don't think it's going to use a lot of memory, you can request 4 gigs. If you're not sure, ask for 20 gigs. And if it fails, it'll tell you it's out of memory, and then ask for more. Everything below that are the commands that'll run. This is your application, essentially. I'm using a variable host and running the command host name. If you do host name on the head node, it would tell you head node 1, head node 2 if you're on BeoShock, or it would tell you Climene or Helios if you're on BeoCat. And we're going to put that into the variable host and then echo out to our output file, hello from, and then that host name. Then I do a sleep for 300 seconds. I do that because I'm going to, in a little bit, demonstrate submitting this, and I want it to stay there. If we didn't have the sleep there, it would run too fast. I wouldn't be able to show you that it's there and then show you how to kill it off. So we're going to submit that. All the output from any script gets put into a slurm dash and then the job number .out file. So that'll allow you to look at the output from any job script. This one will put out very little information, but some could put out, megabytes worth of information. Anything that would normally get dumped to the screen will get dumped to the slurm.out file. So on BeoCat here, I'm going to go to my test directory. And again, that's my hello file there. So to run any script, you just use the sbatch command to submit it to Slurm. So I submit it to Slurm. Now, if it was requesting a large amount of resources, or if there was a lot of stuff in the queue, it might wait in the queue for a long time. Since there isn't, it started running. I also have priority on this node, Wizard 23. That's one of our Intel systems. And the administrators have priority on this one. So I almost always get my stuff through the queue and running on this node in particular. At this point, it says no core is being used because I just started it. The database takes information once every minute. So it'll only get updated every minute with information. So it's now says that I'm running on one core. It still says 0 minutes because it hasn't run for a full minute. My job name again is hello, and this is the job ID number. So since it's sitting there in a sleep for 300 seconds, it would, after 5 minutes, just kill itself off. I wanted to show you again that you can cancel your job manually by using the job ID number. And then we can see again that now I will have no jobs. Okay, I did a listing of uh, everything in this directory, and I made it so that the latest file would be last. So this is the slurm.out file for this job, slurm dash, and then the job ID number dot out. So if we look at that, again, it's very short. We echoed out hello from, and then wizard 23. And then at the end here, it gives me uh, an error message because I canceled it out. It says job, and then the job ID number on wizard 23 was canceled. And now if I do kstat and look at my jobs from just today, you can see I have one called hello from wizard 23. I asked for 4 gigs, and again, I canceled it after 1.5 minutes. So that's a general overview of what kstat or how you submit a job with SBatch. And again, this is a very simple job. Normally you'd have an application in there, and you might want to load modules and do other setup there before you ran your job. And your job would likely last minutes or hours or even days, with 28 days being the max. And also a little bit more about kstat and how we can use that to look at the job. Okay, let's talk about software that we have already installed on BeoCat and BeoShock. And again, mostly the same software will be installed on both environments. A lot of the more common software packages like Python, but also scientific packages, we have already installed so that anyone can just do a module load on that rather than installing it themselves on their home directory. We use an easy build system, so someone has already made recipes for how to build these. I used to have to manually do the installs on my home directory for these, so it's a lot easier now. There aren't easy build modules for everything, so we still, if we don't have it in a module, it's still your responsibility to install that on your home directory. But if you don't see it in a module, ask us first because there might be an easy build for it that we can do easily. And also, if you have to install software on your own home directory, we're always available to help. We expect you to at least start the process, and then when you run into problems, email us, and we're happy to help. So let's run through a few of these, and I'll switch back and do it on BeoShock. We're on head node 2. If we do module avail, that will list all the modules that are available on the system. So you can see some bioinformatics things like BLAST, and Boost. GNU plot is a general plotting package that I'm working with right now. There's languages like Java in there. Let's see, Python and stuff are in here. I may have gone by that already. Yeah, Python is over here. And we have different versions of that. So if you just say module load Python, it is case sensitive. You'll get the default version marked with a D here, which is the newest. If you, for some reason, need an older version, we even have a 2.7 here for Python, which is very old. You can use that. So to load a module, you would do something like if you want to load TensorFlow, which is a Python package, you do module TensorFlow, and then without specifying a version, that'll give you the most recent version. And if you do a module list, this has a lot of dependencies. And so 63 total modules loaded, TensorFlow, and then all its dependencies. So in here is the Python that's built. One thing that I will warn you about, a couple things. These typically use one of two tool chains. The FOSS is the free open software tool set, which is the GNU compilers, for example. And then IOMKL is the Intel compilers, along with the math kernel library and such. So if you want to use the Intel stuff, you would do a module load of IOMKL and use the versions of everything else that are Intel compiled. Otherwise, you can do the FOSS version. The GOMPI is also the GNU stuff. So that's the GNU or FOSS stuff along with the MPI, the publicly available MPI, Open MPI. This loads FT packages and Scalapack and stuff like that as well. Yeah, there's the FOSS package. So loading these modules saves you a lot of time compared to if you have to compile it on your own home directory. TensorFlow is one of those that is a bit difficult to do on your own. And so dealing with the just a module load of TensorFlow, for example, is much easier than having to do it yourself on your home directory. If you're loading multiple packages and in between, it says that it's changing some of the things like the GCC core version. It means that the tool chains don't match up exactly. Most of the time, that's all right. But if you're going to use that set of packages, you may try to load them all with the same dependencies, like all the same GCC core 8.3.0, for example, if you can. Okay, so if you need to install it yourself, I'm not going to go through most of this. Each software package has its own set of instructions on how to configure and install. The basic way is to run a configure script, like it's halfway down here, and then make install. But often different packages don't follow the same methods. So there's just so many different ways to install software these days that we can't cover them all. And often things just don't quite work. So again, it's your responsibility to install in your home directory. And we don't want to install packages that especially maybe only you or your group uses. We try to do modules for software that more people around the university needs. Okay, we have a lot of documentation. And the BeoCat documentation and the BeoShock documentation are at the links above. If you have questions, that's the first place to go. We like to have you at least scan through the documentations before you contact us if you're new to BeoShock or BeoCat. Uh, it's certainly, most people would say, easier to sit down with one of us experts uh, for an hour and let us give you an overview, but we just can't do that with every single person who's new to these systems. So we do want you to look through the documentations. Uh, this presentation and several others will also be on both those sets of documentations that you can look through. Let me just cover some things here that are addressed in there. On BeoCat in particular, we do have priority access if, well, on BeoShock as well. If you purchase a node, you get priority to run there. We manage those nodes essentially for free. That's the trade-off that you get. But then when you and your group members are not using those compute nodes, anyone else in the universities are allowed to use them. That's a great way to share resources, because then if you need more access, excuse me, than is on, then is available on the nodes that you own, then you also can use other people's nodes or the freely available nodes. Both systems have some nodes that are freely available that everyone has priority on. Most of BeoShock is that way. We used to have a large portion of BeoCat that was freely accessible to everyone, equally accessible, I should say. But now we probably only have 15% of the nodes that are that way. Most of them are owned by specific research groups. There are several different parts to the documentation. There's the Linux basics, which covers how to use Linux, but also some information on using each of the different languages that your programs might be in. Slurm Basics gives you the basics of how to submit your jobs, probably in a little bit more depth than what I went over with the Hello World example. And then there's a lot more information in the Slurm Advanced webpage on file systems and array jobs. I will be making a separate presentation that will cover a lot more of those issues in particular. If you need help, you can email beocat@cs.ksu.edu, and that will get you to Nathan, the IT architect that we're hiring, myself, and Seth Gallitzer. So you can email directly to us. It gets into our ticketing system, so it gets logged there, and one of us will reply and help out. At Wichita State University, they have a ticketing system, and you log your problems or your questions with that. That also gets to us, but a copy is also sent to the administrators at Wichita. When you submit this ticket or email to us, give us lots of information. We very commonly get emails that say, I'm trying to run on this node and I have problems, and that doesn't give us anything to go by. So always give us the job ID number as an example. Tell us the directory that you're running from and the command that you're using or the job script that you submitted. And then also the error message that you're getting, do a direct copy and paste or something so that we can see exactly what it is. rather than a description of it. If you're submitting a ticket from Wichita, include your WSUID, because sometimes those come in from a Wichita email address, and that doesn't always include the ID. So other things you can do when you are having trouble, I'll cover some of these more on the advanced presentation as well. The first thing is not listed here is when you get an error code or an error message, Google it. Google your app name and then the error message. Quite often, if it's an error message from a given application, a scientific application, we may not be familiar with that. So the first thing we're going to do is probably Google the application and the error message ourselves. So try doing that yourself. If you're running a job, you can SSH into the compute node that you're running on and use htop and look at what the job is actually doing. And that may help you at times, especially if you think it's running slow or something. That can help you look at any performance issues. We also have a Zoom help session Wednesdays from 1:30 to 2:30, and the link is listed in the documentations, both BeoCat and BeoShock documentations. So you can pop in on that time any Wednesday, and Nathan and I are there. Seth is there sometimes. So it's a good way of getting access to one or more of us. If you're interested in looking into expanding your ability to run or to work in a Linux environment, again, I'll be making a Linux and Bash tutorial as well, but you can always look at the ones online. Just do a Google search for Linux tutorial. If you're going to be operating on supercomputers a lot, yes, you can edit your files on the Windows side and move them over. And the same with if you're on a Mac or a Linux system, you can copy things back and forth. It gets a little tedious. You may want to look into editing files on the Linux side. I use VI or Vim. It's on every Linux system. There is a bit of a learning curve to it. So some people don't like it. I've been using it for over 3 decades, so I don't even think about the commands. My fingers know what they're doing. And so it is very fast once you get to learning it, but it can take a bit to learn. If you want to know more about parallel computing, I will again post another presentation of my own, but there is a good supercomputing in plain English overview that Oklahoma University puts out at the link there. I'm also generating an advanced full-day workshop module that I've put a link to there that you can look at. That's pretty advanced at this point. I will teach that here at some point and advertise that to the people that are on BeoCat and BeoShock. These last two things are getting more advanced. Multi-node parallelization uses the message passing interface, or MPI. Doing multi-threaded computing within one node is done with OpenMP most of the time if you're programming in C, C++, or Fortran. So if you want to learn more about those, the Lawrence Livermore National Lab links, they're very good. Okay, so that's all I'm going to cover in this presentation. So again, I will be posting other ones as well. Definitely take advantage of our help sessions on Wednesdays, If you need to talk to us, we are available. If you want a Zoom meeting with us at several other times as well, you can just email us and say, "Hey, I can't make the help session, or I can't wait that long. Can you hop on Zoom and help me out?" So I hope you found this presentation useful, and let us know if you have any questions. Thank you.